Please go ahead.
Good morning, everyone. It's my pleasure and honor to be presenting my work in this wonderful gathering, and I thank GFC for giving me this opportunity. The topic of my presentation is self-powering smart textile. Initially, I will give an overview of some of the research activities we are doing in our research institute, VGO. After that, I will show you the technological revolution in human history and why we are in dire need of energy right now, and what exactly motivated me to do this research. And after that, I will show you the sensing and energy harvesting principle of one of our sensors, which we developed in our lab. And we have used two different principles. One is piezoelectric principle and another is triboelectric principle. And after that, I will show you the fabrication model of our sensor. And then I will show you some characterization results which we got from our sensor. And then I will give an overview of the whole presentation as a conclusion. So this is VGO's organizational structure. As you can see, our main research and development activities, which are funded by government and also industrial funds, and mainly we are focusing on surface modification using plasma and chemical technology, smart textile, technical textile, composite textile, etc. And the core research and product development areas in our case is surface modification technology using plasma and chemical biotechnology. And we have also developed some parts in automobile and Airbus construction. And currently we are very much interested in working on wearable and smart textiles. We are working on textile for energy harvesting. Also we have made some sensors, for example, in wearable application, pressure, vibration, moisture, thermal sensors, etc. Now, if we go back to history, we will see how technology evolved in human history. For the first time, when the steam engine was invented, people used heat to convert it into mechanical action. And the majority of energy at the time was coal. And as a result, the train came up. And as we progressed, people used mechanical action to convert it into electricity, and that was the Faraday's electromagnetic generator, which was invented in 1831. And as technology progressed and people started, it was automobile and air engine came up, the majority of the energy we were using were oil. Now, as we are progressing, people are doing nanotechnology, microelectronics, IT, artificial intelligence, robotics. What could be the possible next energy we are looking for? As we know, we are surrounded by smart technologies everywhere. We are using smart technologies in homes, in cities, in industries, everywhere. And one study shows that Internet of Things devices increased 31% in just 1 year from 2016 to 2017. And it is around 8.4 billion devices, and it's expected to increase 20.4 billion by 2020, by just next year. So, to power this huge amount of devices, what could be the possible solution? According to Cisco, 90% of the Internet of Things will not be possible if they are not self-powered. So, what's the possible solution of this problem? So, one possible solution could be energy harvesting. So what exactly energy harvesting is? So if you can see, energy harvesting is extracting the environmental waste energy and convert it into electricity. And if you see here, the environmental waste energy we can extract from vehicle motion, from human activity, from radio waves, and we can extract this energy and take it in the form of vibration, light, heat, radio wave, etc., and then convert it electricity to power this Internet of Things devices. Fortunately, there are some available energy harvesting technology taking place right now. For example, people are using wind, solar, thermal, vibration, etc. to convert it into power. And this is the current power density we are achieving from harvesting energy. Now, as we know, all electronic devices does not require similar amount of power to operate. Some electronic devices require higher power and some require very low power. For example, our challenge is in this portion where, for example, quartz oscillator, electronic watch, RFID tag, hearing aid, these all things require very low amount of power. So our challenge is to create some alternate to power these devices or similar power related devices. Now, why textile for energy generation? As we all know, that it's because it's soft, it's flexible, it's stretchable, it's wearable, it's breathable, durable, and washable, and the advantages can go on and on with the textile. There are many possible applications with textile sensors. For example, it can be used in national security, where it can be used to just remote monitoring, and also it's very helpful for sport fitness, where you can monitor the performance of any human being. And also it's very helpful for medical use and healthcare, for example, remote EEG, ECG, EMG, and sorts like that. So, what exactly motivated me to do my research? The motivation was to harvest energy from the environment, environmental waste energy basically, to convert it into electricity to power these small power electronic devices, and also to create an alternate over traditional rechargeable batteries. And as we know, traditional rechargeable batteries is not always compatible with wearable electronics, and also we are very much interested to make this sensor resistant to moisture, chemical, weather, etc. So in a nutshell, what's the objective of this research? The objective of this research is to exploit piezoelectric self-powering textile by converting mechanical waste energies to electrical energy without compromising the flexibility, stretchability, washability, soft-handed and comfortable to use. What exactly piezoelectric principle is? So, piezoelectricity is a property which can be found in some materials where when you press or compress or mechanically deform any material, any piezoelectric material, it generates voltage or it generates charge. So, just like this, if you press or compress this, there is a voltage generation. And below, we show the fabrication model of our sensor, where you can see we have used two conductive textile, and in between we have given a piezoelectric polymer and then surrounded them with a protective polymeric layer. And then we have taken the voltage response of the sensor from oscilloscope. These are some samples we have made in our lab. We have made a different size sensor to see if there is an increase in power generation as we increase the area. Here we have demonstrated if our sensor can be used as a touch sensor, which was seen as we touch the sensor, the LED started lighting, as you can see here. And there is another demonstration we have made in our lab to see how much weight it can detect on the oscilloscope. So we have made this experiment. We have mounted this sensor in this stand, and we have dropped water from here, and as you can see there is a voltage detection, and as we increase the frequency of the water drop, the frequency of the voltage response also increases. And as we further increase the water drop from here, the voltage response stopped. From here we can come to the conclusion that it can only sense a dynamic response, not any static response, and it was possible that this sensor was able to detect less than 50 milligram of water droplet. Here we have made another sensor that was made in our institute, and we have integrated sensor into this belt, and we have mounted this belt on spinning unit of a washing machine to see the vibration, and it really helps us to predict if there is any problem on the machine. We can predict it earlier. If there is any unusual vibration, we can predict it earlier if there is any problem occurring on the machine. Here we have seen that as the area of the sensor increases, the voltage response also increased. Now, the main challenge was to see if this sensor can harvest energy. To do that, we have used a rectifier circuit, and this circuit is divided into 4 parts. Energy source, which comes from our sensor, and then we have converted the voltage response, which is AC into DC, and to do that we have used the diode rectifier here, and then we have used a capacitor to store the voltage that is coming from the sensor, and it was possible to light the LED here. As you can see here, we have mounted the sensor, and then it's a rectifier, and we have used the capacitor to store the voltage, and then the light was lightning, and which is demonstrated in this video. As you can see, the initial voltage was really very low. It was showing almost no voltage, and it was like 0.04 volt, and as we started vibrating our sensor, so as we started vibrating our sensor, the voltage started increasing. And it was possible to light the LED with the stored voltage from the capacitor, as you can see here. Now, we wanted to see how much current can be delivered by this sensor. To do that, we have applied a 1 megaohm resistive load to the rectifier circuit, and we have seen that with different sized sensors, there is a little bit current generation which is delivered to the load, and as you can see, as the area of the sensor increased, the current delivered to the load also increased, from where we have calculated the power as well, and as you can see, as the sensor size increased, the power delivered by the sensor to the load also increases. Now, to further demonstrate, we wanted to see if we connect the sensors in parallel there is any increase of the power. So as you can see, we use different sized sensor basically. So as we increase the number of sensors connected in parallel, the power delivered to the load also increased. Now, currently, we are very much interested in working on another principle, that is triboelectric principle, that uses textile to harvest energy, and this is really our very recent activities we are currently doing, and this is when two different kind of material come into contact, there is a charge generation, and when they are separated by the air gap, there is a voltage generation, and also there is a sliding mode. When they are slide against each other, there is a generation of current, and these two kind of material, one material should be very much electropositive, and another material must be very much electronegative. And here, as you can see, we have made a sample of this principle to see if it was possible to harvest energy even from the sensor. And next, we have demonstrated this idea to see if this idea works or not. We have used a fan basically to create a vibration on our sensor. We have taken out the outer part of the fan and extended it with a hard plastic so that it can beat the sensor. And when the sensor beats, we will see if this sensor is able to store voltage on the capacitor. As can be seen here. And we have applied this sensor to the same circuit, the rectifier circuit. We have used a rectifier to convert the AC voltage into DC and then stored this voltage into the capacitor and then seen the output, capacitor stored voltage output on the oscilloscope, as can be seen here. As you can see, the voltage keeps on increasing as the beater starts vibrating our sensor. So we can, till now we have talked about some variable applications of this energy harvester and sensor, and these are some non-variable applications where you can use it on, for example, on airplane when take off or take on, we can harvest energy from this, and also from the vibrating ship in the middle of the ocean maybe, and also we can power LED signal from passing trains, and also power wireless signals, wireless sensors, and low power electronics. So to conclude, I would like to say that textile itself can be used as a power supply sources for low power energy devices and a great solution for wearable smart textile. And piezoelectric textile can generate and store energy by mechanical action, expecting that we can harvest energy and charge electronics simply by walking. And we have also seen that textile can be used as a self-powered vibration, movement, pressure sensor, expecting to use in predictive machine maintenance. And finally, the sensitivity of the piezoelectric textile sensor has been analyzed by the detection of water droplet, which can detect even less than 50 milligram of water droplet, and from here we can expect that probably one day we can harvest energy not only from the sun but also from the rain. And finally, I would like to thank TCCV for funding this project, which is funded by Austrian Ministry for Transport, Innovation and Technology, BMVIT, BMWFW, and also federal states of Vienna, Tyrol, Vorarlberg, and this is our research institute. It's just 10 to 15 minutes drive from here if you want to visit. And thank you very much for your kind attention.